It is the 15th of December, 1942, and Geoffrey Pyke stands in a cold laboratory in Montreal, staring at a block of ice that has just survived a direct rifle bullet. The American officer beside him is astonished. The ice should shatter into fragments. Instead, it absorbs the impact with barely a crack. Pyke, a British inventor with the unlikely bearing of an academic and the imagination of a dreamer, smiles quietly. He has just proven that the Royal Navy's salvation might lie not in steel and rivets, but in frozen water. Within weeks, his ice will capture the imagination of Lord Mountbatten, Chief of Combined Operations. Within months, it will occupy the minds of the military establishment from the Prime Minister downwards. Project Habakkuk, as it would come to be known, represented perhaps the most audacious and technically daring engineering proposal of the entire Second World War. It was a scheme so ambitious that it straddled the line between genius and madness with such precision that even the men designing it struggled to determine which side they inhabited. The conventional wisdom of 1942 was that the Battle of the Atlantic had transformed naval warfare into a catastrophe for Britain. Germany's U-boat fleet prowled the ocean with devastating effect, sinking merchant vessels faster than they could be replaced. Britain's lifelines of supply were being strangled by a force that seemed impossible to counter. The escort ships available were insufficient. The aircraft carriers that might have provided aerial protection were either committed to the Pacific campaign against Japan, tied down defending the home fleet, or resting at the bottom of various seas after being sunk by enemy action. What the Allies desperately required were floating airfields positioned somewhere in the mid-Atlantic, far from the range of land-based aircraft on either side of the ocean. These hypothetical vessels would need to be enormous, capable of carrying enough fuel and ammunition to sustain continuous air operations. They would need to be strong enough to withstand the battering of the North Atlantic. They would need to be unsinkable, or at least difficult enough to destroy, that the Germans would abandon the effort as futile. No such ship existed. Building one would require countless tons of steel diverted from other military uses, months or even years of construction time in crowded shipyards already stretched to breaking point, and vast amounts of skilled labor that could be deployed nowhere else. The engineering challenges alone were formidable, but the industrial challenges seemed nearly insurmountable. Britain could not build what it needed. America might, but every American warship was already committed to other priorities. The gap between what the Allies required and what they could actually produce yawned like a chasm. Into this impossible situation came Geoffrey Pyke, a man whose previous schemes had ranged from the impractical to the verging on nonsensical, yet whose mind possessed a peculiar gift for seeing solutions where others saw only obstacles. Pyke's fundamental insight was breathtakingly simple, yet profoundly counterintuitive. Ice floats. Ice is strong. Ice is free, requiring only water and cold. If you could somehow stabilize ice, prevent it from melting, and reinforce it with a matrix of wood pulp, you could create a material so cheap and so easy to manufacture that you could build on a scale that would dwarf even the greatest steel shipyards. You could construct a floating fortress so large that sinking it would be economically impractical for the enemy. You could build dozens of them. You could build hundreds. The material itself was self-regenerating. Damaged sections could be repaired by spraying water in freezing conditions. The entire concept inverted the conventional logic of warship construction. Instead of making ships small enough to be defendable and numerous enough to be replaceable, you would make them so large and so numerous that their very profusion would overwhelm any defensive measures the enemy could devise. The material that Pyke and his team developed was called pykrete, named after its inventor with a simplicity that belied its sophisticated engineering. It consisted of approximately 14% wood pulp mixed thoroughly with 86% water, the mixture then frozen solid at temperatures below -15 degrees Celsius. The wood pulp was crucial. It was not merely a filler. The fibers of the pulp created a reinforced matrix that dramatically increased the material's tensile strength. Ordinary ice is brittle, a property that made it useless for structural applications. Pykrete was fundamentally different. When struck, it would deform slightly, absorbing energy rather than shattering. This was why a rifle bullet could punch into it without causing catastrophic failure. The insulating properties of the wood pulp meant that the interior of a sufficiently large structure would remain frozen even as the exterior warmed. Thermal calculations suggested that a hull meter and a half thick would maintain its structural integrity even in tropical waters, melting at a rate measured in inches per week rather than inches per day. The engineers estimated that during a wartime deployment, damage from enemy action would be far more problematic than climatic warming. The proposed vessel, which came to be called the Habakkuk class, was to be colossal. Early designs envisioned a hull approximately 620 meters in length, that is to say, longer than 2 football pitches placed end to end, with a beam of nearly 100 meters and a depth of 60 meters. The displacement would be around 2 million tons, which would make it substantially larger than the largest battleships ever constructed. To put this in context, the ship would have been roughly equivalent in volume to a small city. Yet the cost of construction was estimated at approximately £1 million per vessel, a fraction of what a conventional aircraft carrier cost. The proposed use of the material was as the main hull structure, with a superstructure of conventional materials housing the engines, boilers, and ammunition magazines. The vessel would require continuous refrigeration throughout its operational life, maintained by diesel engines driving large compressors. This was perhaps the most problematic aspect of the entire scheme, for it required a level of technical reliability that wartime engineering could not confidently deliver. Nevertheless, the basic premise was sound. You could construct the hull from pykrete at facilities in Newfoundland, utilizing the abundant supply of cold water available in the North Atlantic. The manufacturing process was straightforward, requiring only forms into which you would pour the slurry and then expose it to winter conditions. The construction would be completed in weeks rather than years. The ship itself would be towed across the Atlantic, refrigeration systems operating continuously to prevent excessive melting. The Allies undertook a serious attempt to develop the concept. A prototype facility was constructed in Canada, and a small experimental barge, 20 meters long and designated the Habakkuk I, was built and tested during the winter of 1943 and 1944. The tests were largely successful, although they revealed certain practical challenges. Freezing a large quantity of pykrete was more complex than the theoretical models had suggested. The slurry had to be frozen uniformly to prevent structural weaknesses. In large blocks, the interior froze more slowly than the exterior, creating stresses within the material. The team developed procedures to manage this, essentially working through the block in stages, but it made the production process somewhat more labor-intensive than initially hoped. The refrigeration requirements proved demanding. The maintenance of mechanical refrigeration systems in the harsh North Atlantic winter environment required constant attention. Yet none of these issues seemed genuinely insurmountable. The British and Canadian authorities were sufficiently convinced of the feasibility that they moved forward with detailed planning for a full-scale Habakkuk carrier. If you are finding this exploration of wartime engineering fascinating, a quick subscribe helps more than you know, and I hope you will join me as we venture deeper into the technological ambitions and achievements of the Second World War. The question of whether Habakkuk would have influenced the course of the Atlantic campaign became increasingly academic as 1943 progressed. By the autumn of that year, the tide of the U-boat war had already turned decisively in favor of the Allies. Improved convoy escort tactics, the availability of long-range patrol aircraft, and the introduction of new anti-submarine weapons had rendered the crisis of 1942 obsolete. The Germans, facing mounting losses and unable to replace their U-boat fleet at the rate required, abandoned large-scale commerce raiding and shifted their effort toward coastal operations and technological innovation. The strategic imperative that had made Habakkuk seem urgently necessary had evaporated. Furthermore, by early 1944, The planning for Operation Overlord was well advanced. It was clear that a cross-channel invasion of continental Europe would proceed, and that this operation would require all available naval and air resources. An enormous floating platform was not what the Allies needed. They needed reinforced beaches and temporary harbors, not ice fortresses in the middle of the ocean. The Mulberry harbors, conventional structures constructed from steel and concrete, would provide the support required for the Normandy landings. They were less ambitious than Habakkuk, certainly, but they were feasible, and they worked. The comparative analysis between Habakkuk and the American Essex-class aircraft carriers is instructive. The Essex carriers, of which 24 were eventually completed, displaced around 36,000 tons and carried a complement of roughly 100 aircraft. They were formidable vessels, yet they required extensive shipyard facilities, thousands of skilled workers, and vast quantities of steel. Each took years to construct. A Habakkuk vessel, by contrast, could have been constructed in months and might have carried 4 times the air complement, though with considerably less armor protection and rather more dependence on continuous mechanical refrigeration. The German response, had the war continued, might have been to develop larger aircraft equipped with even more powerful engines, capable of flying farther and striking with greater force. Yet the sheer economic efficiency of Habakkuk suggested that the Allies could build faster than the enemy could destroy. There was a certain elegant logic to the scheme, though it was logic of a rather abstract sort. The notion that the British attempted to construct ice fortresses was certainly not lost on German intelligence, though their assessment was that the project was propaganda, or the product of British desperation rather than genuine military innovation. The Germans had experimented with various exotic materials themselves, including Torpex explosive charges and new alloys, but they had never seriously entertained the notion of constructing vessels from ice. The concept was too far removed from conventional naval engineering practice. It required not merely a new idea, but a willingness to abandon almost all conventional assumptions about what constituted proper warship construction. This represented perhaps the most significant obstacle to Habakkuk's successful deployment. Not technical challenges or even industrial constraints, but the conservative nature of military establishments. The Navy, whether British or American, had traditions stretching back centuries. Warships were constructed from wood or metal. That was what warships were made of. The notion of constructing a vessel from frozen water seemed to violate some fundamental principle of naval engineering, even if every technical analysis demonstrated its feasibility. The actual historical impact of Project Habakkuk is therefore somewhat paradoxical. The vessel was never constructed. No full-scale Habakkuk carrier ever floated on the Atlantic or sortied to support operations of any kind. In this sense, the project was an absolute failure, a vast expenditure of effort and resources that yielded no practical results whatsoever. Yet the project had profound effects nevertheless. It demonstrated that radical innovation was possible within military establishments, even in the midst of total war. It showed that technical challenges which seemed insurmountable could be addressed through careful analysis and determined experimentation. The research undertaken for Habakkuk generated insights into material science that influenced subsequent developments in various fields. The work on refrigeration and the behavior of ice under stress contributed to fundamental knowledge that outlasted the war itself. Furthermore, the very fact that serious engineers and military figures had devoted substantial effort to the project suggested that conventional categories of thinking could be broken down, that the boundaries of what was possible could be expanded. In this sense, though Habakkuk itself remained an unrealized ambition, the spirit it represented was far more significant than the vessel would have been had it been constructed. Today, the frozen shores of Newfoundland, where the Habakkuk project had been based, contain no monuments to Geoffrey Pyke or his remarkable scheme. The prototype barge has long since melted into the sea. The experimental facility has been reclaimed by the landscape. Yet the concept endures in the imagination of those who study the technological innovations of the Second World War. Here was a scheme so audacious, so technically ambitious, so far beyond the ordinary bounds of engineering orthodoxy, that it could only have emerged from the crucible of total war. Here was a proposal that would have required the construction of industrial facilities of unprecedented scale, the coordination of resources on a staggering magnitude, and the absolute commitment of the highest levels of government and military leadership. Here was an idea that was simultaneously utterly impractical and entirely feasible, a paradox that captures something essential about wartime innovation. The ice fortress was never built, and yet in some peculiar way, it shaped the future of military technology far more profoundly than any actual warship ever could have done. The Habakkuk project stands as a monument to human ingenuity confronted with seemingly impossible odds. It represents the moment when conventional engineering was set aside and replaced with radical reimagining. It was a project that required imagination as much as technical skill, courage as much as calculation. That it was ultimately abandoned for reasons of strategy and practicality rather than technical infeasibility makes its legacy all the more poignant. Somewhere in the decision-making structures of the Allied governments in 1943 and 1944, the men responsible concluded that they no longer needed the ice fortress. They had found other solutions. The immediate crisis had passed. Yet what remained was the knowledge that if Britain and her allies had chosen to do so, they could have constructed floating platforms from ice that would have dwarfed any conventional warship. The very fact that this was possible, that it was not merely fantasy but genuine engineering within the bounds of wartime technical capability, represented a transformation in what the human species could achieve. Here was proof that the extraordinary was within reach, if only the will existed to grasp it. Geoffrey Pyke's greatest achievement was not the Pykrete formula, remarkable though that was, nor the prototype barge, impressive though that vessel undoubtedly seemed. His greatest achievement was to demonstrate that in an age of total war, when resources were stretched to breaking point and the conventional solutions had proven inadequate, there remained always the possibility of imagining something new. The ice fortress that never was remains in the architecture of 20th century history, a towering testament to that enduring human capacity for extraordinary vision.